sponsored seminar. Can everybody hear me okay?
Yes.
So if you don't know me, I'm Allie, our TCO Glimpse. I'm the president of the SPIE student chapter, and it's really our honor and pleasure to be here inviting Dr. Stahl, Phillip Stahl from Marshall Space Flight Center to talk to everyone. And I just wanted to say a few words about the chapter before moving on and introducing our speaker and this wonderful talk that he's going to present. So for anyone who hasn't already heard, the joint OSA and SPIE chapter has received a very honorable recognition recently. We've been nominated for the Excellence Prize through the OSA. We are currently finalists, and at FIO next week, the grand prize will be announced. I will be presenting in a panel discussion during the Student Leadership Conference to show the world all the great things that our chapter does. And so I just want to recognize a number of the students that are here in the audience that have been absolutely integral to the accomplishments of our chapter. And if you see anybody from the chapter wandering around, please give them a congratulations, because we've all done a lot of work, and I think it's really showing. It's wonderful that that we've been able to provide fabulous opportunities to the student body here at RAT. So without further ado, I will introduce our guest speaker is Dr. H. Phillip Stahl, who is a senior optical physicist at the NASA Marshall Space Flight Center in Huntsville, Alabama. And I wish I could say that I met Dr. Stahl while I was there 2 years ago, but Dr. Stahl has been a president, now past president of the SPIE. And so while I was an intern at Marshall, I was never able to cross paths with Dr. Stahl because he has spent a lot of time traveling around the world, visiting with a number of other student chapters all over the place. So we're very grateful that he's taken the time to come here to Rochester and to visit RAT. This is his first time at RAT, and so it's been great that so many labs have opened their doors and have been eager to show Dr. Stahl what we do here at the center and across campus. So currently, Dr. Stahl is leading the study to mature mirror technologies for a new large aperture UV optical and IR telescope to replace Hubble, or James Webb. Previous assignments include astrophysics physicist, Division Deputy Assistant Director for Technology, and the James Webb Space Telescope Optical Telescope Element Mirror Optics Lead, responsible for the primary, secondary, and tertiary mirrors. Just jumping further back in history, he's the leading authority in optical metrology, optical engineering, and phase measuring interferometry. Many of the world's largest telescopes have been fabricated with aid of high-speed and infrared phase measuring interferometers developed by Dr. Stahl, including Keck, BLC, and Gemini telescopes. As I mentioned, he is the immediate past president of SPIE. He's also a member of OSA, a fellow of SPIE, and past ICO vice president. He was elected president of SPIE in 2013. He earned his PhD and master's in optical science at the University of Arizona, and his bachelor's in physics and mathematics at Wittenberg University. So without further ado, Dr. Stahl will talk to us about James Webb.
So I've unmuted that. So I managed the technology development for the James Webb, but the next one that we're going to do after James Webb is actually sort of at the end of the talk. And it's basically, Hubble is a 2.4 meter. We're now looking at like an 8 to 12 meter class Hubble to go up following that. And let's see, the one thing I want to fix is the ICO is the International Commission for Optics. And the only reason I sort of bring this up is I've met with the first years. You guys had such a wide, diverse international student body. that you might know about the ICO. It's the International Commission for Optics, and it's basically a society of societies. It's related to the United Nations. And I am, as I said, your SPIE president, and I say I am your SPIE president because, there we go, SPIE is you. You are the members of SPIE. SPIE exists in the membership, and so I am your president, media past president. And that's not the chart I started to show. Let's get here. Why is this not doing what I want it to do? I want to do something here. I'm going to do this. Do that. I gotta close one more thing. Close that. There we go. I was in the process of hiding and unhiding things. So SPIE pays for me to be here as part of the benefits of student chapters, and there we go. So we have to do the commercial. This is a free enterprise society, right? So as I said, we're at SPIE, and there's some of our students out on the town in Photonics Europe. There we go. We're moving. So SPIE is about 18,000 total members. About 6,000 or so, 1/3, 7,000, 1/3 of that is students. So you represent about 1/3 of the total society. About 40,000 people every year come to an SPIE-related event. And we have currently, and this changes all the time, currently 277 student chapters in 52 different countries. And so this is sort of a distribution of where all the countries are, all student chapters. And I have not been to anywhere near all 277. I've probably been to maybe 30 or 40 of our student chapters. And we have one in South Africa. I don't know where it is, but and I've been to the ones in Australia. Actually, we have one in Perth. There should be a dot over in Perth also. And one of the things that we do is that if you are a student chapter, so this is one of the benefits if you're a student chapter president, so I encourage you to become a student chapter president, is that we take you, we send you to one of our training sessions, and we have training sessions in Brussels, in Prague, or San Diego. Most of the U.S. people tend to go to Europe for their training, and most of the Europeans want to come to the U.S. for their training. So this is a picture of training out in San Diego. The other things we do is for your student chapters, you can apply for activity grants and outreach grants. We provide scholarships based upon merit to graduate students and even undergraduate students. And we're also providing scholarships to go to SPIE conferences. So if you want to go to a conference and you need travel money, you can apply for a travel grant. To give you an idea of where you fit, actually I'll skip forward. So I said we're about 18,000 total members. Inside of New York, there's about 400, and inside of New York there's about 200 student members. We have 4 student chapters, okay? So now you can go and look at how you compare inside of New York. So of the 200 total student members inside of New York, 40 are at RIT. Of the 400 total members in the state of New York, 20 are at RIT. RIT's got 3 fellows and 1 senior member. And those of you in the faculty should be applying for senior member. I think, half of our total membership should be senior members. And you have to also be a senior member in order to be eligible for consideration to be a fellow. Moving forward. There we go. This is one of the things that I think is really important that you should be proud of as an SPIE member, is that we spend 10% of our annual budget every year, our revenue every year, on altruistic activities. So in 2013, I think we spent $3.2 million. In 2014, we spent $3.5 million. In 2015, we're probably going to spend $3.7 million on altruistic activities. That's basically student activities. That's lectures like me. That's the UNESCO Active Learning in Optics activity that we do with the United Nations. That's our scholarships. We provide free digital library to the developing world of your work. So this is something I think you should be really proud of that you're doing as a member through your membership of SPIE. Additionally, on top of that, we spent $1 million on the International Year of Light. And actually, we spent probably about $500,000 on making light more visible, the National Photonics Initiative, which recently resulted in the new Photonics Cluster Center, manufacturing center that was announced here in Rochester. I don't know if you all are participating in that or not, but that's something that we did. International Year of Light, everybody knows we have internet. 2015 is International Year of Light. Don't need to sell that. Good. It's about making light more visible to policymakers and also the general public. So I challenge you, encourage you to get out and do things to communicate to students, high schools, middle schools, whatever, undergraduates, parents, teachers, policymakers, congresspersons, that the importance of light. Light goes from photo emission to photosynthesis, art to architecture, physics to philosophy. And we have put together a whole bunch of learning activities, and there's a website, International Year of Light. There's a hashtag, so get creative. We're only going to have one International Year of Light. And so we also have journals. SPI, we have 10 peer-reviewed journals. One of the things is that we have lots of different communities. We have the bio community, we have imaging community, we have remote sensing. We try to have a journal for each of our major communities. You guys are big into remote sensing, and we actually have, I believe, a remote sensing journal. Applied remote sensing, there it is. And I think you can put movies and things and animations on the online version of that. So some of those are online only. So the remote sensing is an e-journal only, and we can do GIFs and other animations. So if you have flyovers that you want to show. We also have everything is on Digital Library all the way back to 1962. And lots of conferences. So again, you guys are big in remote sensing. We actually have a European remote sensing conference, which is kind of an interesting meeting. I've attended that one a couple of times. And it's tied with the European Defense meeting. Of course, then we have the Photonics West, which 20,000 people, the largest North American optics and photonics meeting, and the defense meetings. So different aspects. We have, for the young people, electronic kinds of things. In fact, our LinkedIn page is getting to the point, I think there's more LinkedIn people now than there are SPIE members. So get involved and become a member. So commercial's over. If I can find my, there it is, my mouse. Kill that. Open this. All right. So who is James Webb? James Webb is the, and why we call it the first light machine. And we'll try not to put anybody to sleep. So James Webb is the first director of NASA. He's the guy who took us to the moon. And the reason the guy named it James Webb, normally if you're in astronomy, you don't name a telescope until after it's had first light. But in this case, the then director of NASA was a big fan of James Webb, and so before we announced the mission, it's called the Next Generation Space Telescope, because Hubble was the space telescope. And then they said, all right, we're going to call it James Webb. And the astronomy community got really, really upset, because traditionally you don't name it. But there's actually a benefit, I think a side benefit, in that it's really hard to cancel a program that's named after the first administrator. And in case you don't realize, it's had some fairly substantial cost overruns. And the first light machine is called that because that's its primary science objective. And so the first light is, the question is, when was the end of the Dark Ages and the reionization of the universe? And what were the first luminous objects? So we're going to go look. So we start with the Big Bang, and that's, so we're out here today, and focus. I was playing with this, got it in focus. So here we are today, back here in the Big Bang, and time expands. And so at some point, the early universe was completely neutral, so we go back to our physics. It was all made up of quarks and subatomic particles, and before you formed electrons and neutrons and protons, the universe is opaque. You can see me because the universe is transparent. You can see me because electrons interact with light and propagate through space. But the early universe was opaque. There were no electrons. There was no light. And so the question is, how did we go from an opaque, transparent, opaque universe, neutral universe, to an ionized, transparent universe? And what were the processes that did that? So in our ionized universe, we can see spectra. In the opaque universe, there is no spectra. And in this process of going from opaque to neutral to ionized, opaque to transparent, you're going to see some spectral patchiness. And these are basically UV spectral lines. But it is so far away that they've been redshifted into the infrared, which is why we have an infrared telescope. There we go. And then the other thing is that, so we have all this matter. Just really weird as to what this thing's doing here to me. New slideshow. I'm just trying to see. All right, it's okay. It was just doing something different when I started, and now it seems to be. Yeah, it skipped. All right. That's where it's supposed to be. It's just really slow. Okay. So again, Kobe looked at the cosmic and microwave background. And so this is the cosmic microwave background for which we got a Nobel Prize at NASA. John Mather, who's actually the chief scientist for James Webb, got the Nobel Prize for Kobe. You know, Hubble looks all the way back as far as it can to pretty close to the Big Bang, you know, to this cosmic dark age. But this is where James Webb science is designed to go. And one of the things we want to look at is in the early universe is these first luminous objects is that where do galaxies flow and how do galaxies form? So these are the filaments of this mass of this hydrogen. So when the universe became transparent, when the universe became ionized, basically you formed hydrogen. And these gigantic rivers of hydrogen come together, and wherever they flow together and they knot is where we get the galaxies forming. And so these are the kinds of things we're going to be looking for, is these universal developments. And so the best thing that we have right now, the only way we know about things right now is we have the Hubble Ultra Deep Field. And so this is a 170,000 second exposure of this little tiny patch in the sky. And inside this area here, there's 47 galaxies that are somewhere between 600 and 650 million years after the Big Bang. And those are just a few examples of them. And the interesting thing is when we look at that same patch with Chandra, is that every single one of those galaxies also has a black hole, which then raises the question, which came first, you know, chicken or the egg? Black holes or galaxies? So it gets back into the question of how do you think black holes form? Do you think that the black hole was there first and it pulled the matter together to form the galaxy? Or do you think that the matter kind of gravitationally came together and got so much there that the black hole formed? And actually, about a month and a half, I've been giving this talk for a couple of years. And all of a sudden, about a month and a half ago, somewhere at the end of July, I realized, I think that the black holes were not only there first, but they've always been there. I'm thinking that the black holes are actually bits and pieces of the primordial Big Bang that are left over of the unionized universe, the opaque universe, because when the universe was very young, it was very dense. It was very, very close together. And so if you have these little itsy bitsy bits and pieces that are in the universe that never ionized, they might look like a black hole. So I called up, actually I didn't call up, I sent John Mather an email, and I said, John, this is, you know, first off, you know, I'm an astronomer, so I'm disclaiming that if this is a stupid idea, just tell me. He said, no, that's actually something that they call primordial black holes. It's one of the science themes for James Webb, is to go try and look and see if we can see these primordial black holes that did they exist before galaxies were formed. And of course, this is a technical audience, so you all know what the Doppler effect is, but redshift is basically just the Doppler effect on light. Is that objects that are really, really, really far away get shifted into the red. And the further away it is, the further into the red it gets shifted. And this is an example of how, say, this object right here, looks kind of red, is that it's about 480 million years after the Big Bang, which is redshift of 10. And you can see at these spectral lines, astronomers for some reason use crazy letters to explain spectrals, which I have no idea what any of those, I think in wavelengths. But it shows up here, and you maybe can say you see it there, but you clearly can't see it at any of those. So that's what redshifting looks like. The further away it is, the further out. So that's the science for James Webb. So let's talk about James Webb. James Webb is first science going to look first light objects, then it's going to look at galaxies, planetary systems, evolution. It's a infrared system. It goes from 0.6 microns out to about 28 microns. It's got a requirement to last for 5 years. It's got a goal to last for 10 years. And we're designing it from an engineering perspective to last for 15 years. Goddard Space Center is the lead. Northrop Grumman is the prime contractor. We're having contributions from the European Space Agency and from the Canadian Space Agency in that University of Arizona, Marshall Reedy, you guys are doing some work for her, is providing the near-infrared camera. The near-infrared spectrometer is all being done by the European Space Agency. The mid-infrared instrument is being done by JPL and European Space Agency collaboration, along with, I think, Marcia's husband, George Reedy. And then the fine guidance sensor is being provided by the Canadian Space Telescope Institute will be doing the operations. I came onto the program in 1999. We'd already been spending money since about 1996. We're currently out here somewhere at the end of 2015, and we're scheduled to launch in late 2018. And this is pre-phase A formulation and implementation. And I actually sort of came off the program in 2012. In 2012, I signed off all the paperwork that said that the mirrors meet specification, that they do what they're supposed to do, and that we can go forward. So, in James Webb, we're spending about $8.8 billion total cost. And I'll say, it's a lot of fun to spend $8 billion. But we don't get to do it just because it's fun. We do it because we're going to try to answer science questions. And these are the key science questions that NASA's trying to answer. How did we get here? Where are we going? You know, what's the start of the universe? What will be the end of the universe? And are we alone in the universe? And so when we started the Big Bang, we looked at those first light ionizations. We're going to look at how do galaxies form, how do galaxies evolve, how do star systems form, how do planetary systems form, and, you know, can we find life? The reasons that we go to space for James Webb are very simple. Well, I mean, one of the reasons why James Webb costs $8 billion is because it's really hard, and it's really hard because it's a space telescope. It's an infrared telescope because it's looking at the early light, and it's really big. We go to space because we got to get above the atmosphere because of the wavelengths we will look at. Is that the atmosphere is opaque in some of these wavelengths in here, and we want to be able to see light. If you're doing UV science, you clearly need to be above the atmosphere here. If you are doing sub-millimeter far infrared science, out here from the 20, 30 microns out to a millimeter or so, you got to be above the atmosphere. So there are certain wavelengths that you really have to get above the atmosphere. And of course, infrared is just heat, but you're a technical audience, so you know that infrared is heat. Why do we need infrared? That sometimes is the other question. And the reason we want infrared is this. Okay? It's skipped. So this is a very famous Hubble image. This is called the Pillars of Creation. It is one of the first Hubble images. This is the same region with the Spitzer, and you can see right through the dust. By looking in the infrared, you can see right through the dust to see the star forming regions. That's why we want to go to infrared. The other reason why we want to be big is we want big and be sensitive. When Galileo back in the 1600s started with his first little telescope of 50 millimeter diameter telescope, he saw the moons of Jupiter. And here's James Webb at 6.5 meters in diameter. This is why you get the result is that, say, 13 exposures versus 400 exposures, you can see things with more photons, more clear. So a little bit of comparison. Hubble at 2.5 meters, James Webb at 6.5 meters, and Spitzer at 0.8 meters. Is that, and here's the wavelength. So Hubble goes from 100 nanometers out to about 2.5 microns. Spitzer goes from about 5 microns out to about 150 microns, I think. And then James Webb is going from 0.6 to 28. So James Webb is going to be 6 times more sensitive than Hubble. But what you want to look at is, say, here at the 1.6 microns, it's got a Landover D of 0.14. At 2 microns, it's got a Landover D of 0.06. James Webb's going to produce clearer, cleaner pictures at that wavelength. In fact, James Webb is going to produce at 2 microns the same quality of pictures that Hubble produces at half micron. At 20 microns, the 0.64, you can see that it's clearly much, it's an order of magnitude better in terms of its resolution than Spitzer, but the field of views are different. And you understand from an optical design standpoint is that, a small telescope has a large field of view, a larger telescope has a smaller field of view at the same wavelength. But Hubble has got the same, Hubble and James Webb are going to have the same fields of view. And the reason is that Hubble is a Cassegrain, 2-element design. James Webb is a 3-mirror anastigmatic design, and the 3-mirror anastigmat gives you a wider field of view. How big is an 6.5 meters? So these are 8-meter mirrors, so you can see the person. And this is a full-scale size mock-up. You can see the person. The sunshade's about the size of a tennis court. And we're going to launch it out to a place called Sun-Earth L2. It's about 1.5 million kilometers from Earth, and it's a gravitational Lagrange point. So the gravitational pull of the Earth, Moon, and Sun system is going to balance the centripetal force that would want to throw it out. So it's all orbiting the Sun, and centripetal force would want to throw it out. Gravitational forces pull it in. How do you put a 6.5 meter telescope into a 5-meter rocket? You have to fold it up. And the reason for the sunshade is that the telescope, because it's an infrared telescope, we want to keep it very cold. In fact, we run it to about 50 Kelvin, below 50 Kelvin. The bottom of the telescope is going to be about 50 degrees Kelvin. The top of the telescope would be about 35 degrees Kelvin, and so that has a thermal gradient. The spacecraft is at room temperature about 300 degrees Kelvin, and we drop about 50 degrees Kelvin with each layer of sunshade. And the spacecraft always stays in the shadow of that sun, the telescope always stays in the shadow. And we have 4 science instruments, the only chart I have in science instruments. The NIRCam with wavelength sensor control. It has also an internal chronograph. The NIRSpec with it has an IFU and a multi-object spectrograph with the shutter, micro-shutter array. The near-infrared camera also does spectroscopy, and then the fine guidance sensor also has a chronograph mode for wide field imaging. So I primarily work over this area. It's 25 square meters of collecting aperture of mirror, about $6 million to make the primary mirror per square meter, or 125 million. So the primary mirror is about 125 million. The fraction limit is 2 microns. The segment sizes are on the order of 1.3 meters. They have to be made to better than 20 nanometers RMS. Very small number of human hair, about 100,000 nanometers. So making it very smooth. This is to give you a relative size of what the mirror looks like with a person. And this is basically 8 or 10 or 12 years of my life summarized in one chart. So when I first came to NASA in 1999, the goal was to try to make the mirrors somewhere around 15 kilograms per meter squared areal density. And Hubble was around 240. There was some Department of Defense telescopes that were around 60. Spitzer was around 30, and so just thinking about it, they had to pull it down. And we spent about $300 million total on technology development, of which about $30 million was spent on mirrors, using the lessons learned from Chandra and Spitzer. We wanted to get our technology to as mature as possible before we started the program. And so we started out with a little half-meter demonstration called the SBMD, and it was a subscale beryllium demonstration mirror that demonstrated the ability to make about a 10 kilogram per meter squared substrate. Then we went to AMSD, which is called the Advanced Mirror System Demonstrator. In phase 1, we had 5 different vendors that we funded, and they produced 8 different ideas. And then we down-selected those to 3 different vendors with 4 different ideas. And then we threw one away. And so we had a glass mirror from Goodrich, a glass mirror from Kodak here in Rochester, and then a beryllium mirror from Ball Aerospace. And we had competitions, and then we eliminated one. So now, someday some of you guys may become program managers and project managers or technology developers. So some lessons learned from a managerial programmatic side. Humans are basically competitive animals. The best way, to get my grandkids to do things, you basically have a competition. If you can trick a 3-year-old to do anything if you make it a race. You can do the same thing with aerospace companies. But in order to have competition, you've got to have 2 things. Number 1 is you've got to have winners and losers. Is that by having a loser, by having someone get thrown off the island, by having, it gets the attention of everybody else. And so you want to start out your program with at least 3 competitors. Because you want to be able to throw one, you want one of them to lose. If you just keep everybody in the game, there's no incentive. The best way to move technology forward, the most rapid and the most economical, is to have competition. We carried these 2 ideas all the way to the end, and we had a technology down select between the 2 mirrors. And because it cost me an extra $10 million to carry the second mirror all the way through to the end, but I probably saved $20 million in program costs. Just in the things that we discovered that didn't work, and the buy-in that the companies put in. The companies, once there's only one person in the game, they have absolutely no incentive to try to reduce their cost. So, big lesson learned from a programmatic managerial standpoint. So we eventually then selected beryllium. The other thing is that you need to program into your plan engineering development units. So engineering development unit, and in fact I would say you need to program in 2, because the first engineering development unit that you build, you're either going to break, or it's not going to work, or it's not going to be representative. And when you're doing a process like James Webb, where you're making multiple copies of mirror segments, it's not until the 3rd one that you actually get a stable process. The first one is not very good. The second one's pretty good. In fact, we're flying the second one, but we didn't have a stable process until we get to the 3rd one. And inside of NASA, then we have these things called NR, non-advocate review, and TRL 6. So TRL 6 basically is technology readiness level number 6. That means you are ready to fly in space. TRL level 9 number 1 is, I just drew an idea out on a cocktail napkin. TRL level number 9 is, I'm flying in space and it works. So TRL number 6 means I've tested this thing as a system or a component in a space-relevant environment, and we think it'll work, and we're ready to go build the real system. Non-advocate review is the NAR. You guys are graduate students. You're going to have preliminary exams, or you're going to have qualifier exams, or you're going to have to stand up and defend your dissertation. It's not quite as brutal as that, but it is in a way. So that the idea is that the non-advocate review is a panel who don't care whether or not you fly. And they have to judge you to say whether or not you're ready to go to space. Just like you have the faculty that judge, are you ready to go to a PhD program? Are you ready to graduate? It's just like that, except that the non-advocate review panel is maybe made up of people that would rather you didn't fly because they want the money you're going to spend for their program. So if you flunk, they give your grant money. Okay, so so that's what we have to do. We have to give all the technology to the TRL level 6 and present it to the NAR and convince them that we're ready to go to the program. Why did we pick beryllium? Mass to modulus is very stiff with a low mass, and it's got 0 CT. This is the real reason. Remember I said the telescope ranges from like 50 Kelvin to 30 Kelvin. Is that over a 50 to 30 Kelvin range, the beryllium changes by 7 nanometers and the glass changes by 20 nanometers. You ever remember what the spec on the glass mirror was? About 20 nanometers, right? So I can't have a mirror that's changed, that is its shape is uncertain depending upon its temperature at the same level as my specification. So that's why we picked the beryllium. This is the, so here's some, walk you through how we make them. We make ingots. This is a big block of beryllium. We slice it in half. We make a primary mirror blank, secondary, tertiaries, and structures. This is some of the people that make the beryllium mirrors at Brush-Wellman. Then we send them down to Axis in Coleman, Alabama, and we machine them out. We throw away about 90% of the material, make them really lightweight. Then we send them out to Tinsley, and we polish them. And this is what a nice clean polished surface looks like. And what I want to say is I actually took these charts out and I put them back in a little bit. The in-process metrology of James Webb is probably the most difficult metrology problem that I've ever worked on in my professional career of this entire generation. And we had a great team of people. We met the challenge, dozens of optometrologists, lots of smart people, young people working lots of hard hours. And it's because we invented two technologies. We invented the 4D space camera, and we invented the Leica advanced absolute distance mirror, and those were absolutely necessary to do the program. My job was to make sure that we didn't have another Hubble problem. So my job was to make sure that the mirrors were made correctly, and one of the things that we did is they had to have agreement. And these are the two technologies that we invented on the program that allowed that to happen. So in-process testing is that we had metrology overlap. If you can't test something, you can't make it. So we had the ability to test and quantify the shape of the mirrors at every single step in the manufacturing process, and with overlapping between the tools, and we did independent cross-checks. So we used profilometry early, we used an infrared Shack-Hartman, and then we compare them. And you can see is that this was before polishing ground. The profilometer is giving us, the CMM coordinate measurement sheet is giving us like 5 micron, and the Shack-Hartman system is giving us about 5 micron. So we take it from a coarse surface with the profilometer CMM down to a certain level, then we hand it off to the infrared scanning Shack-Hartman system to take it down to the point that it's polished, and we can then hand it to the interferometer. So this is the interferometer system. We have the interferometer with the 4D interferometer here with a computer-generated hologram. Here's the absolute distance measuring meter that gives us the radius of curvature. That allows us to completely control the specification of the mirror, the radius of curvature, the conic constant, and the shape of the mirror. Here's a couple of pretty pictures. And so some examples of cost comparison. We had two identical test setups on side by side in the room. We take one mirror, we measure it in one setup, we measure it in the other setup, and compare them. My requirement is they have to agree to 10 nanometers. First time they measure them, they disagreed at 370 nanometers. An RMS of 7 nanometers. They just too much disagreement. Well, what it was is that there's a little bit of backlash in one of the gear motors, and that was the focusing element. And so we had to rebuild the system until we could get it so that we could make these measurements so that you could repeatedly measure the part until you could get it to 10 nanometers. We were able to make the measurement of a part in California, Colorado, and Alabama with agreement at the 10 nanometer level. And then cross-checking is to make sure we got the conic right, is we could do an autocollimation test in order to get radius, conic constant, and clocking. Each mirror is shipped out of Tinsley in its own custom container, pressurized, shock sensors, no more than 2 mirrors per air ride truck, moving truck. At this point they cost $6 or $7 million each. And then they go to Colorado, where they're assembled. This is called the Delta frame. This is called the strong back. There are 2, 4, 6, 7 actuators. Just that we can push the piston, the actuator. We can tip and tilt. We can rotate. We can slide it around. It's a full, 6th degree of freedom. And then the middle actuator allows us to change the radius of curvature slightly of the segment. So we have some ability to control the shape of the mirror on orbit. And we take them to Huntsville, Alabama, where we cryogenically test them in a very large chamber. This is an example, 6 mirrors at a time. We take them down to 30 Kelvin, warm them back up, take them back down to 30 Kelvin, make sure we get the same answer 2 times in a row at the 10 nanometer level. This picture was on the cover of Aviation Space Weekly a few times, or once. And this is the level at which we achieved. Some are better than others. Some are in the 16 nanometer range, 15 nanometer range. Got a couple where, oops, But we have enough margin that's okay. The total figure of the mirror is in the 25 nanometer for the entire primary mirror. And then we take and we coat them with gold. And the red step is the specification, and you can see all the mirrors have a reflectivity that's above that specification. It's actually a protected gold silicon dioxide overcoat. And this is how we move things around the country inside of a C5. And we're now building the mirrors onto a backplane structure. Here's the backplane structure at Goddard Space Center. This is the cover to the carrier. It goes inside the C5. And then we take the whole thing and we put it into a chamber at Johnson Space Center for testing. And the structure actually went into the chamber at Marshall for cryocycling to get any residual stress and strain. So like I said, we take the whole thing down to Johnson. This is Chamber A Johnson. There's a forklift right there. You can see it's the chamber, the door, and the chamber is 12 meters across. The total chamber is about 37 meters high. And so what you can see is that the James Webb is going to hang from the top of the chamber on like a swing or a trapeze swing. So we've got all these vibration isolation with cables, and the whole system just hangs on those cables and be vibration isolated from the rest of the world. And that's how we're going to test it for performance. And then we're going to take it down to French Guiana and launch it on an Ariane 5 European contribution. And so Hubble is in low Earth orbit. There's the moon. James Webb's going out to this point L2. It's about 1.5 million kilometers away. And even though this looks like it's a small space, it really isn't. It's a 1.5 million kilometer by 0.5 million kilometer diameter kind of elliptical racetrack. And so it's a really, really big place in space. See if this starts. There we go. Okay, so first thing we do is we fold the whole thing up and we launch it. And the first thing we're going to do after launch is we've got to get the solar panels out because batteries don't do very well in space. So we need to start generating electricity to the computers. Next thing we're going to have to do is establish communication link back to the Earth through the comms link. So that's the first 2 deployments you're going to see. Once you see that, then we'll start opening up the covers. So here goes the solar panels. Here comes the comm link. And then we're going to start to open up the sunshade in order to start cooling down the telescope. And once we start cooling down the telescope, then you're going to see we're going to push the telescope up away from the spacecraft a little bit in order to get it a little bit colder. The further away we can put the telescope from the sunshade, the better. And then there's 5 layers, so you're going to see us open up these layers, these 5 layers, and then we're going to spread them apart. And that's from thermodynamics. Everybody's had thermodynamics? What's the reason of thermodynamics that you want to have an angle between them? It's a black body radiator. All the heat's going to bounce back and forth between the layers out the deep space. Now, by the way, this movie, if you go look at the movie on James Webb Online, it's not exactly the way we're doing it anymore. It's just I like this movie better than the one that's more realistic. Then we deploy the secondary mirror by 2 rotations and 1 hinge, 3-bar linkage. We block the secondary mirror down, we bring the 2 wings out of the telescope, and that we now have a fully assembled telescope. Okay, so science, in the remaining time I have, I'll go back through the science here a little bit. Science theme number 1 we've already talked about. It's the reionization of the universe. What happens in this region right here? Science number 2 is how do galaxies assemble themselves and form? In the Hubble deep fields, when we look really, really far back, everything's like giant train wrecks. Galaxies are running into each other all the time, and so we want to look at these mergers. One of the things that's interesting on mergers is that actually a friend of mine sent me an email he was reading and said, oh my God, Andromeda's going to run into us, in 500 million years or 500 billion years or whatever it is. What are we going to do? And I said, well, number one is, it's no big deal. It happens, it happens. Stuff happens. I mean, aside from the fact we're not going to be here, but stuff happens, and maybe we'll, as a species, still survive or not. But this is interesting. This is Chandra measurement of 2 galaxies merging in these 2 black holes that are kind of oscillating each other. And when you look at the same data in Spitzer, the same region of Spitzer, there's no heat there. So, these 2 galaxies are merging, but it's not very violent. And it's not like things are running into each other. There's just kind of... Theme number 3 is birds of stars and planetary systems. So if Hubble found the mountains, the pillars of creation, Spitzer found the mountains of creation. This is actually the same nebulae. So this is the Hubble data right there, and this is the Spitzer data, again in the infrared. And what you look at is you can look at stars. So these blocks are all of the stars that exist along these mountains. And these are the stars that are forming. Those are the really, really young stars that are forming. And what's happening is that these stars that have formed over here, their solar wind is blowing against this cloud of dust and compressing it at supersonic pressures, which then causes other stars to form. So here's an example of a shock wave of here's a star that's moving at 20,000 kilometers per second, and it's producing a shock wave that's creating a condensing of the dust out there. Here's examples of stars inside of, I forget what nebula, Ego nebulae. So here's stars forming, and they're clearing out patches of bubbles. They're clearing out bubbles inside of the nebulae in space. Inside the Orion nebulae, this is some Hubble data. Every single one of these images is a star with a planetary system that's forming around it inside of the nebulae. And when we look at Herschel's telescope and we get spectroscopy of what's inside these nebulae, is that there's complex organic molecules inside these nebulae. Everything that we need for life exists out in space. So maybe then how do we look at planetary systems? How do planetary systems form? There's the accretion method, there's big things forming close and move out, or form out and move in. And, we don't really know. All we really know is our own system. And over time, from the 1800s to the 50s to the 2000 to present, we've discovered more and more and more asteroids. So that the point is that dust, asteroids are basically dust. Dust is absolutely ubiquitous in planetary systems. And so let's look at the dust. Here's an example of some dust that's being perturbed by a Jupiter-class planet that's got a slight angle, and it's causing a kink in that dust cloud. This is actually Kuiper belt. This is Pluto's orbit, our own system, and so what you're seeing is spiral arms potentially in a Kuiper belt. And then here's an image of planet formation that's being taken with Herschel. You can see that these rings are starting to clear out as the planets form. And what we really want to do is we want to take images of planets. So this is a planet image that was taken with Hubble, but it was discovered with Kepler. And then we're running Kepler right now, which is looking at when a planet moves between us and a star, the light in that star dips very, very slightly, a few fraction of a %, and we can measure that, and based upon the periodicity of the dip, the Fourier analysis, we can figure out if it's 1 star, 2 stars, or multiple stars. And so right now, what we know is that in our galaxy, there's maybe 100 billion stars, of which there's maybe 17 billion stars like our own. G-class, warm, nice, glowing, yellow stars. In that, we think that maybe every single star in the galaxy has an Earth-sized planet. And so there's probably 17 billion Earth-class planets out there in our own galaxy. The question is how many of them are going to be in the habitable zone, and I will assert also that they need to have a moon. And the habitable zone is basically the zone of which liquid water. We are in the habitable zone, we have liquid water. If we are closer in, we have no water, no life. If we're further out, we're an ice ball, no life. So this is a chart from 2013, which says there's at least 100 habitable zone planets, of which 24 are 2 Earth radii size. This was a chart from 2015, March of this year. An analysis is that there's this Titus Boding law, which was used to predict Neptune before we observed Neptune, which says that planets happen in certain harmonics of orbits, so that you look at the harmonics of the orbits. And so they looked at all the Kepler data, and they looked at the harmonics and figured out where missing planets were. And so they're saying that there's probably another 200 planets that we don't know about. So they're saying between 1 and 3 habitable zone planets. And we just announced this one in July. This is a planet that is about 1.5 times the size of Earth. It has a 385-day orbit. It's about 6 billion years old compared to our planet, which is about 4 billion years old. But this is the closest thing that we have found so far to our own planet. How do we want to talk about habitable zones? Follow the water. Where does the water come from? It comes from the Kuiper Belt, comets, but actually it comes from the star. Stars make water. Stars are like fountains. They are spewing water vapor, hydrogen and oxygen out of the poles at supersonic velocity. This is some Kepler data, it's the spectra, and when they get far enough out, it cools, it condenses onto that dust, and then just snows back down on the planetary disk. So stars produce our own water. So what do we need for habitability? Well, you need a planet that has an atmosphere. It needs to needs water. It needs to have a liquid core so we can have a magnetic field. It needs to have a surface so we can move around on it, unless we're going to be aquatic animal life. How do we find out if we can life? We're not going to look for little green men. You know, we might try to look for I Love Lucy reruns. But really what we're going to do is we're going to look for what is it life does. Life basically eats and poops. It metabolizes. Every single thing that lives on this planet uses one of these chemical processes in order to convert energy into something that's useful, and these chemical processes have byproducts. Water vapor, nitrogen, methane, hydrogen sulfide, ammonia. So we're going to look for spectral lines. The easiest ones to look for is water. The next easiest one to look for is carbon dioxide, but probably the most important one to look for is methane. And so we could also look for, say, if you have chlorophyll, you'll see a red edge. Our planet has a red edge, has a very pronounced signature in the red due to the chlorophyll dip. And you could also, if you had a water planet, you could look for polarization signatures. Light reflecting off of a planet that has water has a different polarization signature than a planet that doesn't have water. And by looking at the chemical constituencies and ratios of these chemical gases in the atmosphere as a function of time, you can understand what the biology is. Is an abiotic, when our planet was abiotic and didn't have oxygen-producing bacteria, it had a different makeup of its atmosphere than it does from today. And you can watch how it evolves. And in order to do that, you need a really big telescope. This is my 8-meter Hubble. But you can also go up to a 12 or 14 or 16 meter. So by having, and with a really big telescope, maybe with the star shade, we can get this kind of imaging of a planetary system. And maybe more importantly, you can get spectra. We can get spectral lines with good spectral resolution of the chemical constituencies of an atmosphere. And the last thing you can see is maybe you can see continents. If you look at the planet long enough, you can see if it's got continents, how the brightness of the planet will change, or the polarization properties of the planet will change as you watch it rotate. Okay, so James Webb is going to look further back in time than any other instrument we've ever flown. It's going to launch in Ariane 5 in late 2018. And it's taking literally thousands of scientists and engineers all around the world to build it. And thank you very much.
So I'll open the floor for questions in just a moment, but I want to let everybody know that there will be a meet and greet mixer with cookies out in the lobby from 6 to 7. So if we don't get a chance to get to your particular questions right now, that will be a good time to ask more questions. So, questions?
So, here, there, and there.
After you finish biting your nails on the launch, what's the next most scary stage?
The sunshade and then the deployment of secondary mirror. If we don't have a sunshade, we don't have a cryogenic telescope. If we don't have a secondary mirror, we don't have a telescope. Actually, and of course solar panels. If you don't have solar panels, you don't have electricity. Because it's clearly the most complicated thing we've ever done.
So the actuators on the back of the mirrors
Yes.
are fairly complex. If one of them happened to break, would the others be able to pick up some of the slack?
Yes. All the actuators have got double winding redundancy, and there are 2 actuators per degree of motion because we want to have the redundancy as well. But if at some point one of the actuators or one of the mirrors became really incapacitated, what we can do is we can adjust all the other mirrors to compensate for that one thing. If we were to lose 2 actuators on one mirror, we would use the remaining good one to drive it out to a large angle and just take it out of the use of the telescope.
What's next after this one?
So the next one that's officially getting spent money on right now is called WFIRST, and that's a wide field infrared space telescope. Its mission is to go study supernovae, to go study the expansion of the universe. It also has a microlensing component, so it's going to do microlensing for exoplanets using microlensing. Kepler was looking at exoplanets to give certain kind of statistics that were very far away. The microlensing will give some statistics of exoplanets that are in close. In fact, I saw a poster, I think, downstairs that somebody was doing some microlensing stuff here. And then beyond that, in 2020, what NASA does is we have these things called decadal reviews, where we ask the science community, what's the most important science that you want us to do starting in the 2020s, and rank it. See, NASA, we don't pick what we get to do. We let the science community tell us what to do, and then we ask Congress, how much money are you going to give us? And then we say, okay, scientists, here's how much money we have. Here's your priorities. We can do these 2 things here. We got enough money to do your highest priority, and maybe we have enough money to do your 3rd highest priority. But we don't have enough to do 1 and 2 or 2 and 3. So we do that kind of prioritization thing. And so there's been 4 missions identified to compete for that next big mission. One of them is called the Large UV Optical Telescope, Observatory Moon Large. It's a Hubble replacement, somewhere between 8 meters and 14 meters in size. The Association for University Research and Astronomy just published a report called Cosmic Birth to Living Earth, which is a call for the science you can do with the Large UV Optical. The other one is a potential mission. It's called a Habitable Exoplanet Mission. Is to study primarily, look for habitable exoplanets. There's something called an X-ray surveyor mission. It's a follow-up on Chandra. Is to do an all-sky survey, wide field of X-rays. And the last one is a far-infrared surveyor mission. So Spitzer is a far-infrared telescope at the 0.8 meter aperture. This would be a far-infrared telescope with maybe an 8 to 16 meter aperture, and again to do survey. So those are the 4 that are going to compete for the next really big thing. And then there's all kinds of little small things here and there. Here, and then anybody else? No, go ahead.
For scientists and just regular citizens that are concerned with the amount of funding that science and NASA is getting, what advice do you have for them?
So number 1 is you talk to the policymakers. You talk to Congress, you talk to Representative Slaughter is a big supporter of science, so it's not a really big hard sell with her. But so get involved with SPI or OSA, do congressional visit days. We send teams of people. We send you to Washington. You get trained in how to go talk to representatives. You basically need to have an elevator pitch. You need to be able to tell a representative in 3 to 5 minutes. That's all their attention span is. No, it's just all the time that they have to spend on any given individual. but you have to explain to them in 3 to 5 minutes what it is that you want to do. So when I was growing up and doing advocacy for a congressional visit case, I would go in and say, you know, I am a product of having a summer job at the Air Force, and I've had students I placed at NASA, and I'm funding students, and I think you need to be spending more money on giving summer jobs to people. Is that the best way to get people to go into STEM is to not teach, is not to tell them how great it is or what a great job, but to actually give them a job and let them experience it for themselves. So that's the kind of thing. So whatever one thing you want to advocate on behalf of, you got to get a nice, crisp story and get involved. Use the professional societies. SPIE, finally, we now have a full-time Washington lobbyist. And that lobbyist is working on the travel restriction issues, working on the Staple Act, which is if you get a PhD in this country, you should get a green card with it. Okay? Because we don't want you going back home and competing against us. It's not in our best interest. The thing about it, we the taxpayer are spending money to get you to advanced degrees. We want to keep you here so you'll be a productive part of our. We're working on rare earth issues. And we're working on manufacturing institutes like this photonic ones we just did. So the professional societies, both SPI and OSA, but like I said, we just stepped up our game. We've got a full-time lobbyist now in Washington working on issues, and we have committees. The E-STEP committee, we like to have students involved in these committees. It's a good way. Even further, we fund congressional internships. Apply to become a congressional intern. You can spend a year working on Capitol Hill. It'll change your life. You know, go work in right now we're funding a young lady, and you don't even have to be opposite. We, SPIE, right now are funding a microbiologist in Representative Slaughter's office. Yeah, so you can apply for those. It's called the Gunther Fellowship, I think, after Art Gunther. Next question.
In the interest of staying on time so we can go to the various labs, and like I said, there will be the more informal meet and greet from 6 to 7. So hope to see you there. There will be cookies. But can we give our speaker another round of applause? And just another pitch for SPIE OSA. We do bring in 2 speakers each year, one through SPIE through the visiting lecturer program, that's how Dr. Stahl was able to come here, another through a similar program through with OSA. So keep an eye on our website. We will have more awesome speakers in the future. So thanks again for coming.